Very good. Okay, to get started with this problem, I'd like to compare the problem we're trying to solve, the finite well, with the problem we've just solved, the infinite well, and see if we can get some, understanding of how these will be the same and how they'll be different. Hang on. All right. For the infinite well, we found a series of bound states. And we found wave functions. And the wave functions looked like this. They went to 0 at the edges of the infinite well. And in between, or inside of the well, they looked like harmonic functions, like sines or cosines. So the lowest wave function looked like this. The next, for the n equals 2 state, looked like this, more or less. The next one looked like this, and so on. Okay? That's what we found for the infinite well. And of course, we found values for the energies as well. What do we expect for the finite well? Well, for the finite well, we expect the following. Inside of the well, we should have harmonic wave functions that look like sines and cosines once again. But outside of the well, instead of the wave function going strictly to 0, we can expect, based on what we found for the step potential, that the wave function will just decay to 0. It won't have to be 0 right at the boundary, but the wave function will leak into the barrier and decaying exponentially. That is, it might look like this. If this is the first energy state, then the wave function might penetrate. We'll have a little hard time with this. Give me a second. Into the barrier a little bit. Okay, so that's what we're expecting. There's no reason that the wave function should cut off and go exactly to 0 at x equals at the boundaries of the well. Instead, they should smoothly approach 0 in the way that the wave function decays to 0 in the forbidden region in the step potential. That's what we're expecting. Here's something else we're expecting. Remember, in the infinite well, we have an infinite number of bound states. We can go to higher and higher energy, and of course, there are more bound states. In the finite well, we expect a finite number of bound states because at some point we'll get to an energy that's above the top of the well, and then the particle would no longer be bound at all. In other words, the wave function would be oscillatory both inside and outside the well. Okay? All right, well, that's what we expect. Now, let's try to set up the problem so we can get started. I'm going to redraw the finite well here. There we go. Okay. There are a couple of things we're going to do, and some of these will make sense when you compare this to the step potential problem that we've already solved. The first is we'd like to split up the space into different regions. But in this case, there'll be 3 regions. The barrier on the left, the well itself, and the barrier on the right. Okay? There's one more thing. When we set up our x-axis, it's going to turn out to be very convenient to put x equals 0, not at one edge or the other edge, but actually right in the middle of the well, like so. This will be at L equals 0. And then to make it comparable to the other one, we'll call the right edge position L over 2, and the left edge position minus L over 2. Okay? That way, the width is still the same as it was in the previous one. All right, that's what we're going to do. Okay, so here's our procedure. First, we'll find the general solutions to the time-independent Schrodinger equation in all three regions. Or rather, in each of the regions, right? That'll actually be pretty easy because we've basically done this already. The second thing we'll do is we'll apply the boundary conditions that describe this problem, all right? That is, basically that the wave function has to match up at the edges of each region. And based on that, we'll find the particular solutions. That match the boundary conditions. And these will be the energy states. Okay? Seems straightforward. But that's what we need to do. All right? So, well, why don't we get started? Okay? I'd like to get a new page, but I want to keep this drawing. So just give me a second while I go to a new page. Paste in our drawing. Well, I'm going to make it a little bit smaller. What? Okay. Okay, there we are. And now we can write down our general solutions. Okay. Here, let's start in region 1. In region 1, we expect psi of x will be the following. So if we're in a bound state, then that means that the energy of the state is lower than U0. It's lower than the top of the barrier. So that's like the wave function in the step potential when we're below when we're in the forbidden region, okay? And in that case, the wave function should be an exponential function, like a e to the excuse me, minus alpha times x, okay? But that's not the only solution. Here's another one. G e to the plus alpha x, where a and g are constants, and well, alpha is this term that we wrote down class ago. We'll write it down again in a second. That's the form of the wave function in region 1. In region 2, we could write the wave function as a sum of terms like e to the ikx plus and e to the minus ikx. But actually, there's another way we can do this. We can rearrange those terms into sine and cosine functions, okay? So the form of the wave function here could look like d times sine kx plus c times cosine kx. So the wave function should be oscillatory within the well. And finally, in region 3, the wave function should once again be exponential. Okay, so that's our general solution. All right, perfect. Well, it looks kind of complicated, right? Look, we have 1, 2, 3, 4, 5, 6 different coefficients to solve for. Yikes, that seems a little complicated. Well, luckily we can use the boundary conditions to start to simplify the problem. Okay, so let's start writing down some boundary conditions. Now, the first of these, the first few might be things you haven't thought of. The first is going to say that if I look at psi of x, well, let me write it like this. The first will say that in the limit that x goes to infinity, as we get further and further away from the well, the wave function has to go to 0. Why? Because if this is a bound state and I'm very far away from the well, then there can't be any probability to find the particle. Okay? Because the fact that we have a bound state means that the wave function or the probability density should be localized around the well. Okay? Thus, if we're looking at a bound state, then the wave function has to go to 0 as x goes to infinity. It follows, of course, that as x goes to minus infinity, the same thing has to happen. Okay? And then there are a couple other results too. These maybe are more familiar to us. The wave function has to match up at the boundaries of the different regions. So for x equals minus L over 2, we require that psi 2 of x equal psi 1 of x. The wave function has to match at that boundary, and the first derivative of the wave function also has to match at the boundary. These are actually two separate boundary conditions. So now we're up to 4 boundary conditions if you're keeping track. And the last set say that when x is equal to plus L over 2, and we're at the other boundary, then once again, the wave function has to match up. As does its first derivative. There we go. And now you can see we have 6 boundary conditions. 6 boundary conditions, 6 constants. We can do it, right? Each boundary condition gives us some kind of equation. And so in principle, we have 6 equations and 6 unknowns. All right? Now, that sounds kind of awful. Luckily, many of these boundary conditions will help quickly simplify this problem, so it won't be anything near that difficult, okay? Here, let's take a look at this, okay? think I'll use red right now. Let's look at the first boundary condition. It says that the wave function has to go to 0 as x goes to infinity. And of course, x goes to infinity in region 3, so we should look at the region 3 wave function, d e to the minus alpha x plus f e to the plus alpha x. And if the function has to go to 0, that means that f must be 0. Because if f was non-zero, then as x goes to infinity, the wave function would blow up. But the boundary condition says that it can't. Therefore, f equals 0. Likewise, looking at the second one, for negative infinity, we can see that looking at this wave function in region 1, that when x goes to negative infinity, this first term, would you mind if I do something? This is really awful, but I actually just want to change the sign of these two terms. I know it's easy for me to do, but if you're writing in pen on paper, it's hard, but I have my own reasons. Okay, there we go. Going back to wave function 1, you can see that as x goes to minus infinity, this term here blows up. So that means that because of boundary condition number 2, g must be 0. All right? Perfect. So now we don't have 6, we only have 4 equations to work out and only 4 coefficients. All right. Well, we could go ahead and solve it like this, but actually in this problem, the way we've set it up, we can actually make things much simpler if we use one more principle, a principle of symmetry. Okay? Hang on. Let me talk about that. Okay, we can use symmetry to simplify our problem. Okay? We were very careful to set this problem up to make u of x symmetric about x equals 0. Okay? So u of x is equal to u of minus x. Okay? And the consequence of that is that if u of x is symmetric, then the probability density of the energy states also has to be symmetric. And you can think of that for this as arising from this consideration. Imagine we have the symmetric potential, and then we find the probability density. Okay, everything looks good. And now we solve another problem where we just take our potential and flip it around. We change plus x to minus x. And look at the probability density there. Well, of course, because the potential is symmetric, when we flip around the problem, we have exactly the same problem that we started with. So the solution has to be the same too. That means the probability density must also be symmetric about x equals 0. And what that means is that it means that the wave function itself must have either even or odd parity. That is, it must either be like this, psi of minus x equals psi of x. In other words, symmetric about x equals 0. And this is called even. Or it must have odd parity, where psi of minus x is equal to minus psi of x. Odd. Okay? Now, so we can look for even solutions, or we can look for odd solutions. Eventually, we have to do both. But if we start by looking at one of them, let's say we look at look for even solutions, then we can simplify things even further, okay? So, for example, for even solutions, it must be the case, if we go back up here, looking at the wave function in region 2, it must be the case that b is equal to 0. Why? Because sine is an odd function. And so you can't add an odd function to your solution if you want the answer to have even symmetry. On the other hand, cosine is an even function, so no problem there. So for even solutions, b goes to 0. No contribution from the sine function. And the other thing we find is that if the solution is even, then a must equal d, so that the amplitude of the wave function is the same on the right side and left side of the well. Okay? There we go. So now we had 4 free parameters left, and we've just gotten rid of 2 of them. So we're only going to have 2, and that's not going to be hard at all. All right. Here, let's just write down our new set of equations, and then we'll stop, okay? Sorry, I'm skipping around like this. I'm sorry. So our general solutions now are not quite so general solutions. Now say that in region 2, side 2 of x is equal to c times cosine kx. And in region 3, side 3 is equal to, I believe, I'm trying to remember what I called my coefficient here. Oh, d, excuse me, d times e to the minus alpha x. Okay? And then we have 2 remaining boundary conditions. The first is that psi 2 at x equals L over 2 is equal to psi 3 at x equals L over 2, and psi 2 first spatial derivative at L over 2 is also equal. There we go. So we've written down our problem now, and then we've used the boundary conditions, including symmetry, to simplify things to a problem that's going to be fairly straightforward to solve. Okay? Fairly straightforward. There's still one big trick we'll need to do. All right, let's stop this video and we'll continue in the next.